Part 2 on this review has to do with what we call the ideal gas law, which relates the pressure, the volume, the number of moles, and the temperature of a gas. This R is a constant, okay? And the reason why it's the letter R is because it's the gas constant. That's what R stands for, which I have labeled right here. This equation comes from combining the gas laws of Boyle, Charles, and Avogadro. If you combine all three together into one, this is what you would get. So we're just combining all of these together. So to look at, and we'll look at some problems. Now, the thing about the value for R, the gas constant, it has two different numbers that are typically used. The only difference between them is the unit for pressure. This one is in atmospheres, this one is in kPa. So it's just because we have so many different units for pressure that they have two different units for the R constant because of the different pressure values. And those are the two most commonly ones used. They usually don't use PSI since that's an English unit. So we'll have to keep those in mind when we use this equation. So here is one example. At what temperature will 6.54 moles of neon gas occupy 12.30 liters at 1.95 atmospheres? Now, how do you know you're going to use the ideal gas law with this? Well, notice this one. Is there a change in the variables as far as like what the initial temperature is and the final temperature, or the initial pressure and the final pressure? No, there is not. Since there isn't a change in variables, then that would tell us a good sign right there that we are looking at the ideal gas law. So the ideal gas law is that equation, PV equals nRT. Now, in this one, they're asking us at what temperature. So we want to do temperature, so we want to isolate temperature. So I would divide by NT. So it looks like my equation is going to be our NR to equal T. So I just do a little algebra there to manipulate that. And then all I need to do is fill in my variables. So my variables for this would have been the pressure is 1.95 atmospheres times the volume is 12.30 liters over the number of moles I had was 0.654 moles times the R constant. Now, since this is in atmospheres, I'm going to have to use the one that has atmospheres in it. And so it is over moles times Kelvin. So moles cancels. Atmospheres are going to cancel, liters are going to cancel. I'm left with the units Kelvin. I do my math, I got 446.7 kelvins. Go to sig figs, it looks like there's three, there's 4. We go with the least, so it looks like 447 Kelvin. Now, if they would ask it, they just said temperature. They didn't say Celsius or Kelvin, so either one would be correct. It didn't ask for a specific unit. So that's one sample of a problem. Here's another problem. So it's kind of a continuation of the ideal gas law. So the problem, there just says, determine the volume of 1 mole of gas at STP. So since we just have this, and then if we have something at STP, don't we know standard temperature? Isn't this 0 degrees Celsius or 273 Kelvin? We have to be in kelvins. And then pressure, isn't pressure 1 atmosphere? Correct? So I have pressure, I have temperature, I have moles, and they're asking me to find volume. So I'm not having a change of initial to final, so it must be this equation. Now, they want volume. This is the one they want, so I'm going to divide by P here. So there's my equation. Volume equals nRT divided by P. So if I plug in my numbers, I have 1 mole of this gas times R, and I'm going to stick with 1 atmosphere for my unit, so that's going to be 0.0821 liters times atmospheres over moles times Kelvin. You know, there's a lot of units to that. And then the temperature is 273 because it's 0 degrees Celsius over 1 ATM. This cancels, moles cancel, Kelvins cancel, I'm left with liters. Doing my math on this, this comes out to be 22.4 liters per mole. That is our conversion unit for gases at STP, and this is only at STP. This is what a gas occupies, 22.4 liters for every 1 mole. I am doing a lab that you will watch, and I figured out from my lab data what it was. I was slightly off, about a 6% error, but it would not matter which gas I collect. This is the constant. So this is our conversion unit for gases to get to moles. So you should be able to go ahead and do the worksheet on the ideal gas laws. So one other thing just to think about, it says, did the warm-up question describe any particular gas? No, it did not. So this applies to all gases. And just comparing what we know about a mole, don't we know 1 mole is the molar mass, and that would be grams for a solid of any substance, whether it's a compound or an element. A mole, we can also relate it to particles, how many particles are in the container. And then I'm going to show you that lab experiment, and now we can say 1 mole of any gas, therefore at STP, because we know if you change the temperature and pressure, it does change the volume, is 22.4 liters. So just one more sample. What is the volume of 3.5 moles of carbon dioxide at STP? What's nice about this is we're at STP. So at STP, this is our conversion, right? So if I just take 3.5 moles of CO2, and I'm at STP, that's what it said, times, this is the conversion factor, for every 1 mole of any gas, there are 22.4 liters. So that would be just my simple conversion. When I do the math for this, it looks like I get 78.4 of CO2. So that would be how we can use our 22.4. But we have to make sure that we have converted our gas to STP conditions. Because typically in the lab, we don't collect always at STP. We collect at other conditions, and then we have to convert it to STP to make this comparison. So you should be able to go and do the worksheet on the ideal gas laws.